Hi, today we are going to talk about coordinate systems. This is the last section of chapter 3 on vector addition. So we have talked about the Cartesian coordinate system and the polar coordinate system. The Cartesian coordinate system is a coordinate system that you are familiar with of plus x, plus y, x, negative y. The polar coordinate system is the system we've been using with vector addition, with 0 degrees to the right, 90 degrees up, 180 degrees to the left, and 270 degrees down. But there are two other coordinate systems that we need to become familiar with. They are the terrestrial coordinate system. The terrestrial coordinate system is a coordinate system that is based on north, south, east, and west, with north as 0 degrees, east as 90 degrees, south is 180 degrees, and west is 270 degrees. And we also have a system called the cardinal coordinate system. And the cardinal coordinate system is a system that still has north, south, east, and west, but it gives reference angles. So a line that's coming up like this at 30 degrees is called 30 degrees northwest. So we want to learn about how these systems work. So the first thing you need to recognize in the terrestrial system is that it runs in a clockwise direction. And as we are moving from 0 to 90 to 180, we are working opposite what we're doing in the polar coordinate system, which is running in a counterclockwise direction. In the cardinal coordinate system, we are saying something like 30 degrees northwest, but there's also a complement to that, which is 60 degrees west of north. And so what we do in this particular system, we have modified our language, but the word of should be in here. So when I say 30 degrees north of west, that helps me understand that I start in the west and I go 30 degrees towards the north. And you could see here, I start in the west and I turn 30 degrees towards the north, and that would be 30 degrees northwest. Same thing happens with 60 degrees west of north. I go to the north and I turn 60 degrees towards the west. You go to the second letter and you turn so many degrees towards the first letter. Now, these systems we can use in vector addition. We run into vector type problems all the time. And what we want to recognize is that the easiest way to do vector addition is to get into the polar coordinate system. And then once we're in the polar coordinate system, we can convert easily into the Cartesian coordinate system using r cosine theta and r sine theta for the values of the x component and the y component. And so or I hat and j hat. Remember from the last video, we talked about the idea that I hat represents the x component, j hat represents the y component. And so we can use these equations here if we're in polar coordinates and always get the correct sign. So how do we get from cardinal and terrestrial to polar? Well, we draw a picture. So if I have an angle that says 40 degrees southwest, and I want to get that into the polar coordinate system or the terrestrial coordinate system, I draw this value. So here's my initial axis. It says southwest, so I go to the west and turn 40 degrees towards the south, and that's 40 degrees southwest. Once I have 40 degrees southwest drawn, I can now imagine an overlay of the polar coordinate system. So in the polar coordinate system, this is 0, 90, 180, 270, and I am going 40 degrees more, so that makes 40 degrees southwest equal to 220 degrees in the polar coordinate system. If I want to find the value in the terrestrial coordinate system, 0, 90, 180, 270, it's 40 less than 270. That was our 40 again, And so we end up with 230 degrees in the terrestrial coordinate system. And that's how we do that. We could then try going from terrestrial. Let's say I have a value that is a little more paper here. Okay, let's say I have a value that is 115 degrees in the terrestrial coordinate system. So 115 degrees would be, again, 0, 90, 180. So 115 is down here. It is, if this is 90, 115 is 25 degrees more. So when I put this into the polar coordinate system of 0, 90, 180, 270, that makes this 360. I am going back 25 degrees from that, so that makes that 335 degrees PC. 360 minus 25. And if I want to put that in the cardinal coordinate system, I'm down here 25 degrees. There are two possible answers to this. We usually use the first one, which would be a southeast bearing, which would be 25 degrees south of east. So I go to the east and I turn 25 degrees towards the south. But I also could use here, if I wanted to, I could use 90 minus 25 or 65 degrees east of south. Again, we usually use southeast, southwest, northeast, northwest. So if I can convert into convert from system to system and get into the polar coordinate system, then I can do a vector addition problem. So I could say something like 5i hat plus 8j hat plus 100 and, well, maybe not 100, maybe 10 at, we'll use 100 degrees PC plus 60, or let's use a different value. Let's use 6 at 60 degrees southwest. Okay, so I have this problem here. What this says is to create a vector table. So my first vector is 5i hat plus 8j hat. My second one is 10 at 100 degrees PC. My last one is 6 at 60 degrees southwest. I'm in all sorts of coordinate systems here. So if I have I hat, j hat, that means that I already have, let me fix this up here. That means that I already have the x and y component for that one. So the x and y component is 5 and 8. That's our I hat, j hat value. It says 5i, 8j. The next one, I'm in PC, so that's good. The PC angle is 100. And so 10 cosine, the I hat value is cosine. So 10 cosine 100, and I get negative 1.7. And then the next one is 10 sine 100. And in that one, I get 9.84 or 9.8. And then I need to do this 60 degrees southwest. I need to convert that because I want it in PC. The magnitudes don't change. It's just the angles that's going to change. So this will be 6 at, and the angle will be southwest 60 degrees. So I go to the west and I turn towards the south 60 degrees. So 180 plus 60 is 240. So 240 degrees PC from 0, 90, 180. So I'm going 60 degrees more. And so now I do 6 cosine 240. And again, if I have it in PC, I don't have to worry about sines. It immediately comes out negative 3. And I do 6 sine 240. Again, I'll get the correct sine, which is negative 5.2. And so I add together my x's and I add together my y's. And from there, I find the value in Cartesian coordinates. This would, whatever I get here, is my Cartesian answer. Now, if I want to put it back into PC, so to go from PC to Cartesian, from PC to Cartesian, I go and do I hat is equal to r cosine theta, and j hat is equal to r sine theta. But how do I go from Cartesian back? Well, that's exactly what you do every time you get to this point. To get it back into PC, you're going to use r is equal to your x component value squared plus your y component value squared. So your I hat, j hat value. So r ends up equaling a value. And then theta is always y over x. So it's the arctangent of your y component divided by your x component. Remember that if you are in the first quadrant, you add 0. If you're in the second quadrant, you add 180. If you're in the third quadrant, you add 180. If you're in the fourth quadrant, you add 360. This one here looks to me as if it is in the, this would be a negative value, this is a positive value, so it's in the second quadrant. And so if you are in the second quadrant, you would add 180 to the negative answer that you get here. There are some problems to practice online. You're going to want to do that. You are going to have to convert between Cartesian, polar, and terrestrial coordinates, and you're going to have to convert between polar and Cartesian back to polar. If you have any questions, let me know. Have a wonderful day.